Hello developers, let's start developing. Today we're taking on task 12 of the 2025 Advent of Code. But today is not the 12th of December, it's actually the 14th. And why didn't I solve it on the day off as I did with all the rest? Well, I can come up with excuses, but the truth is I was scared of the task. And this was quite a wild journey, and there is a trick, and I will show you the trick. And I managed to go deep inside the rabbit hole this time, so whatever the intent of the creator was, so good one. You got one over me. Yeah. So yeah, I managed to basically fall for all the tricks. So what are all the tricks? Well, let's take a look at the task. So the task is that we are given some kind of Tetris forms and we need to fit them inside of a grid. So I read that and I said, oh, this is a packing problem. Those are kind of hard. We're gonna need to have some recursion, some backtracking. They are very, very much NP complete. But if we have this many shapes, they are solvable. Or if the shapes have some specific properties. And they give an example how we can basically fit two items to shapes like this inside of it, so it's gonna fit. Everything is else, some examples, some other regions, and yeah, we need to just count all the regions. And then I saw the input. So first of all, I saw the size of the inputs, and the input is that we have basically somewhat less than a 50 by 50 grid, which is huge. That's 2,500 cells, and we need to fit that many items. That's not 0 or 1 or 3 or 5, that's a few hundreds that we need to fit. And if you've ever worked with recursion, you know that 200 tries is a lot of backtracking and this will never end. And of course I tried to use some Excel to help me. And note that for these shapes, they are not only in that position, but they can be rotated and they can also be flipped. So basically, this first form has 4 options and 2 options and 4 and 4 and 8 and 8. So in total we have 30 different shapes. But and that means that we're gonna need to have a recursion that is 30 shapes wide and 200 shapes deep. That kind of goes something like, yeah, back of the envelope calculation, that is gonna be 30. Oh no, we don't cannot use this one, we need this one. It's gonna be 30 to the power, no, 30 to the power of 200, let's say. So yeah, this number is way, way, way bigger than the number of atoms in the observable universe. So this is, it's gonna be a number with something between 300 and 400 zeros, and that's kind of huge, so we're not gonna do it that way. And the beautiful thing, we don't do it once. So this would have been hard, but this would have been kinda impossible. And that's where I got scared and I started, so I'm gonna think on it a bit later, And I started playing around some more in Excel, and to be honest, at this point I was on the right track. but I didn't finish it because I didn't see it. So I said, let's see if we can eliminate some areas. Some areas that are sure to fit or not fit the pattern. For example, let's say we have a 26 by 26 table. Yeah, so this thing is a 26 by 26 table. And if we have, I don't know, a T-block. Yeah, let's paint this yellow. And we have our 26 by 26. Let's paint that another yellow. So if we have to put some answers are kind of obvious because this thing has 5, so to say, points, and this thing has 26 times 26. This thing has 667 points. So the question is, can we fit 3 T's within our field? Sure we can, because it's 3. Doesn't matter how we put them, we can just put them. So that is one part of the equation, so to say. But the other part, the part that I thought of myself, so to say, is can we put 200? So can we put 3? Yeah. Can we put 200 of these? Well, it's kind of an obvious no, because 200 of these will be 1,000, and 1,000 is bigger than 676, so that's a no. So what I did was basically count how many points each of these elements will take. So this will take 7, 7, 6, 5, 7, 7. And I did something like this. So the full area of the grid is that much. And we got lucky. So we need to put in 307 pieces with a total area of 2017. 2017 is more than 2016, which means this is not feasible. So we know the answer for this one. We don't need to calculate any kind of recursion, any kind of things. So this is a simple no. And it turns out that there are around 500 of these. So about half of the areas are no's, which means we're halfway there. So we don't need to solve this 1,000 times, we need to solve it 500 times. And let's look at the percentages. So let's sort by percentage. So this is the percentage of for those that are feasible, which percentage of the grid will be left unfilled. And you can see that the smallest percentage we have is about a quarter, which means about a quarter of the dots somewhere will be filled. And this is where I got so far. And today I was looking around a bit, discussing it even with Claude a bit, and Claude proposed that, oh, we're gonna need this kind of a solver and that kind of a solver, but it's not gonna be feasible. Can you divide the area into 10 by 10 pieces maybe, so we can solve them, and so we can make a solution that will only take a couple of minutes per line. I don't think that we were gonna get there, but it started me thinking. We managed this part, the obvious no's, but is there a point when we can see what is the lower bound or something like that for an obvious yes? Can we fit something else inside this rectangular area that we know that is gonna fit? So which is we can say that the maximum number of things where we are sure that we cannot do is gonna be, let's say, this, we're gonna put in some number over here. So it's gonna be this time times 5 minus this. So if this is positive, where did I put it? Yeah. So if this is positive, we get a no for sure. So 100 is a maybe. 120, that's a maybe. 130, also a maybe. 140 is a hard no. And we can see 135, maybe. So 135 is a maybe. We have no idea whether we can put 135 t's inside this area, because 135 t's take up 675 spaces. Maybe it's possible, maybe it's not. But this is the sort of question that research papers are written about. So I didn't feel that it will be quite easy to solve. So, but anyway, we know that anything that's 135 plus is gonna be a hard no. And we know that anything up to 30 is going to be a hard yes. And between them, we're going to have an area which is a maybe. So, and that maybe is a problem. So let's see what the yes area is. I think that we can fit 4 t's here, or 5, or 6. Or you know what we can do? We can get a bounding rectangle on this. So we can make this t into a rectangle. Because if we can fit the t's side by side, that gives us a very reasonable lower bound. And it's not dependent on the t. We can draw a bounding rectangle on anything. So let's see if we can do this. So it's 3 by 3. We can do it 1, we can do another one, 3, 4, 5, 6, 7, 8, and there's not enough space for another one. So we can have 8 in this direction, and we can have also 8 in this direction, which means that we're gonna have to, so the lower bound is 64. Of course, we can fit 64 without any effort. We can just put them right next to each other. We don't need to flip them, we don't need to do anything, we can just put them. So we have now that 0 to 64 is a definite yes, 65 to 135 is a maybe, and 136 and up is a hard no. So we're in a position when, yeah, we can solve these trivially. We can solve this trivially, but for this we're gonna need a degree in math. So what can we do? Let's see how many of our input are in the maybe class. So, yeah, I upgraded my Excel a bit. So we have, this is the top level thing. So this, the area comparison. So this will either say no or a maybe. And this is the fitting part. So this will also either say yes or a maybe. When we join them, so this is going to be a no, this is going to be a yes, and we will have a maybe only if both of these say, I don't know, maybe. Let's see how many maybes we have. In our input, we have exactly 0 maybes. And that is the beauty of this task. If one of these is even one of these, if this was not 27, if this was 37, for example. Now this task is unsolvable because we have a maybe case. And what's even worse, looking at the demo input that we have, in this scenario, all of these are maybes. all of these are maybes. Let's see with the 4 of 4. We need to fit two p's, basically. Two things like that. That's a p in Cyrillic. Can we fit them? It's 4 by 4, so it's 16, and a p is 1, 2, 3, 4, 5, 6, 7. So 14 is less than, is more than, 16 is more than 14. And we can trivially put just 1. So this is a maybe. And this is also a maybe, because we cannot, and this one is also a maybe. So all of them are maybes, and that's why I got thinking about the maybes, how to solve the maybes, not how to solve the yeses and the nos. Anyway, now when I know that we don't have a maybe in our input, well, I can just write the code. I haven't written it, I haven't solved it, but now I think that our biggest problem will be actually parsing the input. So we're gonna have our input type is gonna be, what do we call them? Shapes. Those are an array of strings. They're not an array of strings, they are let's have them as a dot or hash array of arrays. And next we have, next we have our regions or areas. Regions. So a region is something that has a width, a height, and not x and y, but it has shape counts, which is an array of, actually a number array. So, and we have an array of those as well. So this is the input that we need to do. This is gonna be some ugly code, so I will pause this 15-minute round until I get the parsing running, and then we will just show it. So I did manage to write some ugly code. I have no idea whether that it's running, but the idea is basically this. We have a shape regex which catches this part of a shape, and then we are basically looking for that line. Once we have that line, until we get to an empty line, we just read them, split them into individual characters, and save them until we run out of matches for this, because this line won't match this pattern. And after that we just slice off everything that we already processed, and then we basically process the regexes with this pattern. We have the width, the height, and then a set of numbers. We split them and we splice them, and we might get something. So let's try this, since we're not doing any kind of processing, which means we can even use the smaller input because it's, well, smaller. Otherwise the smaller input just lies to us. These are all maybes, and we don't want maybes. Maybes are hard. Anyway, npm start debug 12. Let's see what we get. And we got an invalid region line, which is 4 times 4. What do you mean this doesn't match our regex? Yes, I think I made a boo-boo. I tested the regex on... No, this matches our regex 4, 4, and... do we have a space or something like that? Invalid region line. So, but it is a region line because which kind of means that we got to the regions. Whoa, 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 whoa. Yeah, I let Copilot generate this, so no, don't push it to the regions, just return this. I don't know why, but it always wants to do for reaching while I want to do mapping. So we're gonna calculate the regions. We are calculating the shapes one by one. So we do have this line on the set of shapes, push this next shape. But for the regions, we can just map everything and directly set it. I didn't even notice that we don't have a return before the throw. So this actually true because it wanted to throw. So we have our shapes, we have our regions, and we cannot really see the interesting part, that is the shape counts and the content. But the width, the height, and the indexes, all of them were read correctly. So yeah, let's do this. From the input shapes, actually we can do it like this. We have shapes and regions, and then we can say for each shapes dot map shape to its content, and then those we get only the contents, and for of each, yeah, content of these print matrix of the content, and then an empty space. So let's see if we have them correctly. So we have this data, let's compare it to whatever we had. This is the small input that we're working with. So we had, yeah, that is 0, that looks like 1, that looks like 2, that looks like 3, that looks like 4, and that looks like 5, which means that our shape parsing seems okay. Now let's just see if we have our region parsing. So for each of the regions, dot map the edge region from region to region dot shape counts. Yeah, print out the counts so just we can see them. We have 0, 0, 0, 0, 2, 1, 0, 1, 0, 1, 2, 2, 0, 1, 0, 1, 3, 2. Okay, let's now do the same thing for the big input, because the big input had some two-digit numbers, whether this thing works with two-digit numbers. It's quite a common error that you make something that only works for a limited amount of sizes. Yeah, there's 1,000 of these, so we're gonna need to scroll to see if we have everything. So we are starting with 4359, we're ending with 2830. So that's all there is. It seems that our input is properly parsed, so we're gonna stop this. So now we just need to run our no and yeah thing. So how do we run it for no's? For the no's, we need the total array of all the shapes, so we need to have the shapes area. No, totally not, except the part when we're actually mapping. So we're mapping each shape. We need to map each shape to a number, basically. And so the shape's content, Actually, we need to first to sort. I'm gonna skip that. Technically, there's nothing that stops us from having this in our input. This is shape number 2 and this is shape number 1, but we don't have that in our input. So I'm not gonna worry. We need to map it. We need to sort it here and then map it, but I will just map each shape. So for each shape, we're gonna take out the content, and actually we only care about the content. Yeah, we just destructure it directly, so we only have the content. And for each of the content, so the content is a matrix. The content is this. Yeah, that is a matrix of those. And basically what we need to do, we need to count the D's. So for each row of the content, yeah, we need to do this. Map each row to a row that only has the hashes, and get its length. So this will map our input to 322, and then we just run a sum method, which is actually reduce, which will return the correct one. So yeah, we're gonna make that into a one-liner. And yeah, let's log the shapes areas. I will turn off debugging. Let's just run it. So the shape areas are the ones that we actually need. And now for each region, we will filter out all the regions. So yeah, we're gonna filter out all the no regions. So we were left with the maybe regions. Give me any region where. Let's calculate the total area of that. Yes, something along these lines. This is the total area of the region. So let's go back to the Excel. That is this thing, which is multiplication of the width and the height. The width and the height. Otherwise, we're gonna get the shape counts, this thing, and then for each of them, multiply them with the specific shape area. And when we do that, we're gonna sum. And that's exactly what we're doing. We're summing that with that, that with that, that with that. If we go here, yeah, you can see it a bit cleaner. And then what we do, so yeah, we have the total area, we have the feasible area. So the feasible area is feasible if the shapes area, this is not a equal sign. So if the shape total area is bigger or equal to the shapes area, then it's a maybe region. Otherwise, it's a no region, and we don't count no regions. So since we know that we don't have false regions, we can just do this. Everything's that not a no, we know that it's a yes. So yeah, this will be our processing. 457. This will be our final answer. But let's be honest. So we will count how many of these maybes are actually yeses. We're not gonna do that, but the format is something along these lines. So we have our region, and let's get the bounding rectangles for all the shapes. The bounding rectangle for all the shape is literally 3 by 3, but let's calculate it. Bounding width. So I'm going with the th is gonna be for the shapes. Yeah, bounding. Take all the shapes, takes the maximum length of the first row. Yeah, we can do it with any row, but let's not go overboard, and then get the maximum. For the bounding height, take the maximum width. So this will be the bounding width and the bounding height of a shape. If we have a rectangle that has that width and that height, then we can fit any shape inside of it. And now let's count how many shapes we can fit inside of it. So fits, actually let's call this width. Width fits is how many things fit widthwise. So that means that we're gonna take the width of that region and divide it by the bounding width. And then we're just gonna do a math floor, so that we get the actual integer number. So if it's 26 and we have 3, we can fit 8 of them, because 8 of them are 24 and 2 are left over. Whatever's left over, it's left over. And we're gonna do the same thing for the height, and we're gonna see if how many total we can fit in that with that approach and how many shapes we have. If total fits is bigger or equal to the total shapes, then yeah, we have a yes. But actually what I will also do, true maybe regions are these where this doesn't hold. When we have total fits is less than the total shapes. We don't actually need the yes regions. Actually, yeah, let's have them. And now I will just say if true maybe region's length is bigger than 0, then throw an error. Further checking not implemented, because that's gonna be complicated. Otherwise, return the yes region's length. So if everything is okay, nope. We should get 457, and we got 457, and I'm quite confident that when we go here, we're gonna get a star for part 12. Yep, everything seems cool. One of the very, very few times when I was sure of the answer before I pasted it in. But it is what it is. This was a very nice trick, and I spent a lot of time thinking long and hard about how to actually fit these shapes on that kind of thing, and the answer was staring me in the face the whole time. So I love you, Eric Wasdell, that the guy that creates these puzzles, and you got me this time. Don't forget to click like, subscribe, whatever you want to, and keep developing.